So just one more thing here with this graph, this x-intercept. Now look, I want you to be the person that, even if maybe we're going to some new territory, that you can use an old strategy, plug in 0, of course, plug it in for y, and I don't know, I guess we'll kind of see what happens here. You got to solve it. You got to solve it for x. So it's kind of like an algebra equation. Subtract 1, divide by -2. Subtract 1, divide by -2. And we get 1/2. Okay, I skipped a couple steps, but you get 1/2 equaling e to the x. When x is in the exponent, okay, that's kind of like a new place for x. It requires a new method. When x is in the exponent, you have to use a log, okay? And as I kind of say, you have to slap it with a log, okay? Because when you slap it with a log, the exponent comes tumbling down. Do you realize what kind of log you need to slap it with if it's e to the x? I'm sorry, what did you ask? What? Yeah, what kind of log? It would be a natural log. Okay, now a natural log, without going back through like all the theory behind this, a natural log is going to cancel with a base e. That's because it has a base e. But the bottom line is, when you have e, you use natural log. Okay, now remember over here, I kind of had log divided by log. That's because these logs did not cancel out. So I end up with log divided by log. But over here, one of my logs cancels out. So I'm just left with a natural log of 1/2. You know, something you punch in your calculator. Make sure you can do it. Natural log of 1/2, it comes out to be -0.69. And again, you're just using your natural log button. -0.69. It even makes sense, because if you look at your graph right here, that x value is negative. That would be the main reason it makes sense, because you have a negative x value. Anything that's happened here with logs that you have a question with? Anything with just the graph? In your assignment, you will also be asked to find everybody's favorite domain and range. I thought we would do that at least for one problem. But I hope that you realize that the work you did with the graph is going to help make the domain and range pretty easy. Okay, because the graph, as far as its direction, goes forever to the left and right. It goes forever to the left and right. That means the domain is all real numbers. All of these graphs have that type of domain. Because just think about it, that means I can plug in any number I want for x. That means I can have any exponent. Right, I can have any exponent negative to positive infinity. The range is always restricted by your horizontal asymptote. So we know the graph's below that horizontal asymptote, just need to say so. Say it the right way. Remember, if you're below 1, that means you're from negative infinity to 1. Like, say negative infinity first, because you always put the small number, then the big number. So I'm below the horizontal asymptote, and that restricts your range. These also have range restrictions. As you can see, it's based on the horizontal asymptote. All right, that's kind of a crash course in exponential functions. I'm going to kind of just pull another little trick out of the bag here. It's something else that has to do with exponential. And it's kind of a little standalone. It's not a graph. It's not an equation. It's actually the idea of changing a base. Let me just show you, because sometimes people are like, what is this? It's just a little exercise in thinking about how to change a base. So it's not an equation. It's not a graph. it's 16 to the 3x. If you want to call it something, it's an expression. 16 to the 3x. And you'll see some of these in the assignment. Obviously, that's why I'm kind of picking it out, because it's kind of special. The directions will say something like change the base to, and then it'll tell you, like maybe change it to base 2. So we want to change it to base 2. Okay, and here's how this goes. You just have to think about what base you have right now, 16. And then you have to kind of say to yourself, but I don't want it to be 16. I want it to be 2. Now, you're a smart group. You realize you can't just, just make it 2. Okay? No, I'm going to make it base 2. It still has to equal what I started with. Now, I rewrote 3x because it still has to equal what I started with. So I guess the question here is, how can you think of 16 as a base 2? In other words, 2 to what exponent is 16? 2 to what exponent would be 4? We're just changing the way we think of 16. We're changing it to base 2. Specifically, we're changing it to 2 to the 4th. Now, kind of the reason for this little escapade here is so you can do something with these exponents. Yesterday, we talked about a couple of those rules. Remember what to do when you have like a power to a power? That's the situation where you want to multiply. So we get 2 to the 12x. Multiply. Okay, and if you're kind of looking for like what's the purpose of this, 16 to the 3x is the same as 2 to the 12x. Okay, just because we changed the base, but we followed the rules. So that's a little something with exponential. The exponential model that's up on the screen, that's not up on the screen, it kind of takes on a application version. The application version is this arrangement of fun stuff. V equals C, 1 plus or minus r to the t. V equals C, 1 plus or minus r to the t. It's the same letters, okay? In other words, like the same like positions in an equation, just with some meaning. So it's still y equals a b to the x. We kind of still have like those 3 things. Thanks. Okay, C, let's start here. V, value. It could be the value of money. It could be the value of bacteria. It's whatever like the final value would be. Let me put that word final value. Okay, maybe like kind of like the answer to the problem. C is the initial value. Now that shouldn't be a big surprise to you because that's what we said is true about A. You know, it's like the initial point. Okay, and then we have this 1 plus or minus r, which honestly is kind of like the main thing here. Now, 1 plus or minus r is still the base. In other words, the whole 1 plus n minus r is the base. But r is broken out. It's broken out because r represents the rate or the percent rate. The percent rate. So what's happening here is we see that the percentage is always added or subtracted with the number 1. And if you think about it, that's what's supposed to happen. You're either greater than 1 or less than 1. So the percent is always add or subtract with 1. If you put that together, you still get the base. The time just needs to match the rate. The time just needs to match the rate. What I mean by that is if you're growing by some percentage per day, then the time is in days. If you're growing by some percentage in seconds, then your time is in seconds. It's just, they just have to match. I want you to try a problem. I always find this to be helpful, just to say, if you look at page 25, number 23, do you see something old? Do you see something, kind of like you've seen years ago? Do you have to do something new? Maybe it's something that you don't quite remember, but take a look at number 23. It's a little word problem, and just honestly, it's kind of like a good old standard exponential word problem. Just a nice standard exponential word problem. Use the formula that I gave you. Can you plug into it? And can you even get that calculator fired up and maybe even get an answer? If you want to look, whenever you want to look, here's the setup. How's that matching? Did you put the starting value and the final value in the right place? You don't want to reverse those numbers. Did you change the percent to a decimal? Just good basic stuff. Did you choose a plus sign? Did you choose a plus sign? It's growing. It's growth. Are you solving it for t? Think algebra. Do some algebra, solve it for t. Okay, you have to divide by 500,000. You can't multiply 500,000 into the base because the base has an exponent. So we just divide it, get the number 2. And I haven't shown this yet on my calculator, but when you slap this thing with a log, when you slap both sides with a log, you obviously get log, you get log, but you also get the t to come out front. So it kind of like always works this way. You divide the logs. Just got to divide them in the right order. But I divide the 2 logs. Log of 2 divided by the log of 10375. Thoughts, concerns. Remember, don't I don't want you to think that I think you should already know this. I mean, I'm kind of going over some stuff that normally kids have some questions with, but it might look familiar. Okay, now exponential is always percent. So as soon as number 23 said that there was a percent change, I'm allowed to use this formula. Okay, exponential always means percent, or percent always means exponential. There's kind of another common type of percent, which is why it's exponential, and it makes for another good application problem. Okay, now look, that's a lot of stuff on the screen. I don't think you copy it all down, but if you're taking notes, you might want to still have some information. This is a half-life problem. Yes, we can think that it relates to chemistry, but you don't have to pull out any chemistry notes. I want you to realize before we do anything else that half-life means 50% decay. Because basically, if I'm going to have half of what I started with, I'm going to have lost 50%. So it's a percent problem. Okay, now there's a couple other little pieces up here, right? We've got this idea of 14 days. Basically, 14 days is the half-life. So we can kind of make note of that. And then what's going on here? 10 grams initially. So the initial value is 10. And I guess it even is asking for when are there 3 grams? When are there 3 grams? Okay, we kind of have the important stuff. That's the idea. We've got it's a half-life problem and some information about time and amount. Okay, we should be able to plug into the formula, and that's why I gave it to you, so you plug into it. I mean, what do we got? An initial value of 10. We've got a decay of 50%, so, choose a subtraction sign. 0.5. 3. Okay, now we can think of 3 as the final value, kind of like the V. We're trying to find out when we get to 3. Here's the thing, though. If we just continue to plug into this formula, and I suppose maybe kind of haphazardly plug 14 in for the time, we kind of have to scratch our head and like, what is the variable? Like, what are we trying to find? Okay, and this is where we got to think a little bit more about, okay, what's really being asked here? When you put T up here, when you think about T, it's always got to relate to the percentage. The percentage is representing each cycle, each half-life cycle. Okay, so I go through one half-life cycle. What was 10 now is down to 5. I go through another cycle. Okay, what was 10 went down to 5, went down to 2.5. Oh, wait a minute, I only need to go to 3. So what I'm saying here is that T is not days. T is not equal to 14. T is equal to a cycle, a half-life cycle. And if you kind of think about it, that's what we don't know. We don't know how many cycles it takes to get to 3. It takes one cycle from 10 to go to 5. It takes another cycle for 5 to go to 2.5. Now we can solve for it. Okay? Kind of the same thing. These kinds of problems, I don't know if they're fun or not, but it's kind of the same thing. You divide, you end up with a similar position here, a similar place. That is a time to use a log. You're going to use a log because the x is in the exponent, because the variable is in the exponent. Okay, make sure you're okay. Make sure you're okay with like dealing with the decimals. I think you're going to take the log of 0.3 divided by the log of 0.5. So the log of 0.3 divided by the log of 0.5 gives you 1.7, 1.7, dot, dot, dot. Okay, that would not be the best final answer, because I'd kind of say to you, like, what does that mean? Is it 1.7 days? And that would be silly, because it takes 14 days just for a half-life. So as I said, this is like the number of cycles. We've gone through 1.7 14s. We've gone through 1.7 times 14. You can convert that into days. Okay, and that's kind of a little extra step, something just that you got to think about based on what it means to be cut in half. And you get 24 days. Okay, so there's some word problems kind of awaiting you in this section. There's actually one other type of word problem that will use your calculator's regression command. Now, we actually did this a little bit with linear, with some linear stuff. I just want to go over it with you so you realize it's the same thing. On page 22, there's a table of populations. You might feel like you kind of have done some of this before, but I'm suggesting that we can take a table of data and we can do a regression. A regression is when you come up with an equation. Okay, basically it's pushing a couple buttons on the calculator. So, and you actually will end up doing this on the test that's coming around the corner here, just so you realize that this isn't something just kind of for fluff, but I hit the stat button, I go to stat edit. So I hit the stat button, I go to edit, and we're at this place that maybe you recognize, L1, L2, and we have to put the new data in. Now, sometimes students aren't sure how to clear out the old data. Depends on what you've done. You can type over top of the data. Okay, so I could type in 1880. I could type over top of the data, or I could hit the delete button. If I hit the delete button, it'll one by one delete the values in there. By the way, I'm plugging in the actual 4-digit number this time. Last time we did this, I plugged in a 1-digit number, and I'm kind of doing that on purpose because I want you to realize that you could do it either way. If I decide to plug in the 4-digit numbers, I have to realize that my X, or my time, is in that unit. Okay, so we go to stat, edit, L1, L2. And really the only other thing that I want to show you here is if we're going to do a regression and we want it to be exponential, we just need to say so. So we're going to do an exponential regression. I'll tell you what, I'll show you that button, but it's never a bad time to talk about the window, because I know it bugs kids. If you push the window button, you kind of need to think about the numbers you just typed in. Now, I typed in numbers from 1880 up to like 1970. I know I've done some problems where I made those numbers bigger. You could make them bigger, but this time I'm going to say maybe I'll just choose that sort of range of numbers. And then for the Y values, I plugged in like 50 all the way up to 200. I am going to choose to start at 0 and go a little bit past 200, so I'll go to 300. These numbers, though, they're not just like a guess. I'm kind of looking at my table, and I'm making them similar. Now remember, the calculator is not going to graph all that data you typed in unless you tell it to. Second y equals. Second y equals. And it's kind of like the stat plot setup screen. All I really need to do is choose number 1 and turn it on. When I turn it on, it tells the calculator to look in L1, L2. Okay, which of course is where I put those numbers. Okay, if you have the favor of the calculator upon you, you get a little graph. And it might even look kind of exponential. In other words, it starts to grow and grow, of course, more quickly. Now listen, this is what I really wanted to show you. When you do the actual regression and go to stat calc, keep on looking, and you'll see at the bottom, at least on this calculator, exponential regression. Exponential regression is going to like find the base. It's going to find the starting value. It's going to do a b to the x. I know some of your calculators are a little different, like you have to push a few more buttons to get it to do that. Just go through that screen. I just want you to realize what you have. Okay, what you have is a really small number. That's kind of weird, actually. You have 3 times 10 to the negative 11. Okay, but then you get this base of 102. You get this base of 102, and you still have an exponential equation. By the way, the reason this number is so weird is because I typed in those large 4-digit numbers for 1880, 1890. So it had to go way back in time to come up with this number. But anyway, look at the base. The base has 2% growth. 2% growth. Okay, because the number that is greater than 1 is 0.02. And that represents 2%. That's actually pretty common for population growth. It grows right around 2. It's actually about 1.9%. Okay, I kind of just made that problem up. Remember, you could plug numbers in here. If it was a question on your assignment, you know, answer a prediction question, something like that. All right, now, a little different, but that actually finishes up that section. You actually solve some of that section when you opened up your book. It's just a couple questions about graphing, and then it's some application problems. I do encourage you to get started on it. Okay, I know you just finished one, but I encourage you to get started because tomorrow we'll be talking about the next section. Okay.